Good morning. My name is Pareto Front. I'm a senior researcher with KWR Water Research Institute in the Netherlands. I'm very happy with this opportunity to talk to you this morning about digital technologies for asset management. First, I'd like to introduce my institute to you. So we are a non-for-profit research institute situated in the center of the Netherlands. We have 10 Dutch shareholders and 1 Flemish shareholders, which are all water companies. And we have about 180 people working on different aspects of the human or urban water cycle. About 135 of these are researchers. Many of them have PhDs. Some of them have affiliations with universities. We work in a number of joint research programs, including a national joint research program, EU-funded research programs, but also consulting projects, etc. And we're also part of many international networks and collaborations. Our motto is bridging science to practice, trying to bring the new developments from academia to actual practical application. So what am I going to talk about to you today? Well, basically, I want to talk about some digital tools which help you to do 21st century asset management. And I will include some examples from the work of KWR, both from the research side and from the actual application side. So first, I'm going to discuss our philosophy on designing and maintaining assets. I'm going to talk a little bit about obtaining data for effective asset management. Then I'm going to talk about the design of pipe and sensor networks and the tooling you can use for that. I'm going to share a number of case studies with you, discuss trade-offs, and then come to the conclusion. So what we like to talk about is what we call intrinsically smart networks. Of course, we all know what smart networks are. They are water networks that have been fitted with sensors or sensor platforms in a broad sense, that have a data transmission infrastructure, that have data analytics, including modeling and maybe machine learning, that allow you to do interventions based on data. What we call intrinsically smart networks have all that, but more. They have a smart design of the pipe network itself. They have a smart design of the sensor network. So if we can compare the traditional smart networks to the nervous system of the infrastructure, then we can compare the intrinsically smart networks to the entire body, which includes the nervous system. So, and practically speaking, some examples, for example, a smartly designed pipe network may have a self-cleaning capacity in the sense that in all parts of the reticulation networks, the velocity of the water reaches a certain level every day so that particles that may accumulate are washed away, and there's no risk of having water discoloration. Smart pipe networks for us also include the creation of network blueprints or master plans based on solid principles that guide the evolution of your network in the coming decades. It also includes the application of numerical optimization techniques to determine optimal network layouts, optimal pipe sizing, but also transitions from the current structure to the optimal structure we would like to have in the future. In terms of the sensor network and analytics, we think about the condition assessment of pipes using sensors and robots. Again, here also the application of numerical optimization techniques to design sensor networks is very important because they allow you to investigate the trade-offs between investment and information yield of your sensor networks. So first, I'm going to talk a little bit about these robots, and then we're going to move on to numerical optimization of the network and of sensor networks. So at KWR, we have been working for a number of years on a concept of autonomous inspection robots that are intended to live in the distribution network and continuously gather data about the condition of pipes. Why would we want to have that? Well, we know that inspection technologies which are available today are cumbersome, are relatively expensive and usually applied only to small parts of the network. With this concept, we have a tool that continuously gathers information about practically all of the network, allowing a solid information basis for asset management decisions. The robot itself, the further development is in the hands of a commercial entity now. I'm not going to talk more about that. What I want to talk about more is how you can be sure that such a technology is safe to be applied in a real network. Because of course, with new technology, you can always expect that there to be teething problems. So you want to be sure that these robots, when you put them in the network, they're not going to fail. You won't have to open the ground on several locations just to dig it up again. So in order to make sure that these technologies are safe to be used, we constructed a test network at our KWR premises, which consists of about 400 meters of pipe in a combined meshed and branched network topology with several pipe diameters, multiple materials, and all of the complexities that you expect in a real network, that you expect such an inspection tool to encounter in real networks. And a lot of control on the hydraulics, on the composition of the water, etc. So these are a number of pictures of the facility. We see this is the outside part, black building in the background houses the inside part with the pumps and the electronics, etc. And as you can see, it's a really complex but representative network, which allows you to do all kinds of testing, but which is still very accessible. So if there's any problem, you can easily open up the network and retrieve the tool. So this is a map of the network, which you can see has both the meshed and the branched structure, has all the materials which are listed here, and quite a complex topology. So like I said, we built this network to be able to test inspection robots in particular and inspection tools in general. But of course, there's so many things which you can do with such a network. You can do all kinds of tests on sensor networks, spike testing, optimization and processing, algorithm testing. You can also do process research, look at the accumulation and resuspension of particles in such networks, research biofilm formation, etc. So this is really an opportunity for the research community, and we're very open to collaboration and facilitating third-party work in this facility. The next thing I wanted to talk about this morning is design tooling. All water companies have experts that, based on their experience and using hydraulic simulations, are capable of creating network designs that generally work quite well. But we know from research that there's a lot of room for improvement, that these networks and these systems are so complex that even highly trained and very experienced experts cannot see all options and are not in a position to create actually the best design of such a system. So in order to help these people, we have created a software tool called Gondwana, which stands for Generic Optimization Tool for Network Design and Operation, which allows you to do all kinds of numerical optimization using evolutionary algorithms on various aspects of drinking water networks, which can include the design, the hydraulics, the sectioning of the network, sensor positions, etc., in single or multi-objective settings. So we have a standalone tool. We are finalizing a web tool as well, which we hope to be able to share with partners. So I'm going to discuss a number of case studies which have used Gondwana, and which demonstrate how such a digital tool can support smart asset management. And the examples I'm going to discuss have been our work by my colleagues Ina Vertomme, Karel van Laarhoven, and Claudia Quintiliani. And the first one deals with the design of a smartly designed pipe network. So, of course, the structure of a network is one thing which needs to be considered, but the sizing of pipes in such a network is also a very important question. What I'm showing here is the network map of one of the cities in the south of the Netherlands. And in collaboration with the local water utility, we have applied our optimization platform to this network to see how the current layout of the network could be improved. Trying to minimize the volume of the network, which of course is a proxy of the cost, while maintaining or even improving the hydraulic performance of the network. And I'm going to come back to that later on. So what we see here is the optimized design of the network, which means for all the pipes, an optimal diameter has been ascertained, which is indicated here. More interestingly, on the right-hand side, we see the differences between the current layout and the optimized layout. So we see that many pipes can have a smaller diameter, indicated in blue, if a smaller number of pipes is increased in diameter, so in red. And this would actually result in a network which has a volume which is 35% less of the current volume, which means a lot cheaper than the current layout. It's better because in the current situation, there are quite a few nodes which have insufficient pressure at some points during the day. These are indicated by the colored nodes here. And our optimized design has very few of these nodes with a smaller magnitude as well. So what we see here is not only that we can have a network which is cheaper, but also performing hydraulically much better. The reason that there are still some nodes which have substandard pressure is because we have allowed that in the optimization with a small penalty. We could also have said it's not allowed to have any substandard pressures, and the design would have been slightly different. So the second case study I want to discuss with you is about transitioning towards an optimal design. Of course, when you have your current layout and you have a plan for what it should look like in the future, the question is how to get there. And this is something which, of course, you can approach in a pragmatic way, but this is also something which you can be subjected to numerical optimization. And if we do numerical optimization, we can think about objectives like minimizing customer nuisance, but also maximizing the increase of network performance during the early years of the transition. Well, on the right-hand side, you see an example of a result of such an optimization in which the letters indicate the phasing of the replacement of these pipes year after year. And the important thing is that during this process, all hydraulic requirements are continued to be met. So that's part of the optimization. There will be no periods during the transition in which there are additional substandard pressures, for example. So the third example I wanted to discuss is about the design of virtual DMAs. The drinking water companies in the Netherlands have in the past built large open networks with a high degree of meshedness, so to say. And they are currently thinking about or starting to implement more DMA-like structures in order to reduce non-revenue water. But they don't want the cauliflower structures, which are very common in many countries. They want to keep their open network layout, for example, for reasons of security of supply, continuity of supply, and water quality. So they're looking to have open virtual DMAs in which all boundaries are fitted with a flow meter, so that the net in and outflow, net inflow of a DMA can be determined. Of course, if you're going to do that in many locations, you're going to be paying a lot for a lot of flow sensors. So actually they want to have the smallest number of flow meters possible. But also, if you want to have effective leak detection, it would be good to have many DMAs, which means small DMAs, which means a large number of flow meters. So there's a very interesting trade-off here. We've done a project, or actually multiple projects, with the utility of Dmas, which supplies the area of The Hague and surroundings. And I'm just going to share a couple of results of this exercise with you. So what you see here is a complicated figure, which on the left side shows a Pareto Front. This shows a set of optimal solutions for a combination of two objectives. And the first objective is to minimize the number of boundaries, the number of flow meters on the horizontal axis. And the second objective is to maximize the likelihood or the capability of detecting leakages, which is related to the net boundary flow of a DMA. So if we go to the left, we have fewer boundaries, but we have worse performance in terms of leak detection. That's the trade-off we're looking at. And all these dots indicate a solution, a subdivision of the open network into DMAs, which has an optimal combination of these two. So this is very insightful for the people of the water utility. They can investigate the trade-off between these two parameters and decide for themselves if introducing a number of extra boundaries to increase the performance is worthwhile. And this is something which they've enthusiastically done, and they've selected this design to be implemented in practice. So of course, you don't need to put flow meters on every boundary if you close a number of these boundaries by closing a valve. And that's the final step of the design which was performed. We tried to see which of these boundaries should be fitted with a flow meter and which could be just closed while maintaining an open network structure, maintaining water quality, maintaining security of supply, and limiting the drop of pressure experienced by customers. And again, this is an optimization problem, and we showed that maybe half of these boundaries that were identified can actually just be closed while preserving security of supply, instead of putting a flow meter there. So this was a very interesting result for Dmas. We did a somewhat similar exercise for the utility of Brabant Water, which was putting pressure sensors in the network to be able to detect bursts. And they were already working on it, but realized that we were working on numerical optimization. So we joined forces and we helped them to determine how many sensors they need and where they should put them. And again, we have some kind of a trade-off situation in which here on the horizontal axis, we see the number of connections which are covered by the sensor network, which is a proxy for the part of the network in which you can actually see or detect bursts. And on the vertical axis, the number of sensors. So as you increase the number of sensors, you increase the coverage of your sensor network. And again, this allowed the water utility to investigate the trade-off between investment and return on investment in terms of information yield and come to the best decision. So this was an interactive process working at the utilities office, and it resulted in a lot of insight in the functioning of the hydraulic network for the people working at the utility. So we came up with the optimal locations, with the trade-off, and actually Brabant Water was very happy with the result. They said all in all, the project didn't take up a lot of time, created a lot of unexpected questions and answers, gave us a lot of insight in the hydraulic system, and resulted in an amazing optimized result for the locations of their sensors. So that's a very good example of how these research results come to a practical application. And well, I'd just like to stress this. I've been talking about it in some of the examples before. Doing multi-objective numerical optimization is really a unique tool that allows you to explore your options, to explore how much extra performance is gained by investing a little bit extra. So to conclude, I think that smart 21st century asset management is supported by digital tools because they allow you to design your networks and to design the transition to the best performing or maybe the most resilient or some other parameter network for the least cost. They allow you to actively and directly investigate the condition of buried pipes, to know the condition of buried infrastructure and act accordingly, to optimize sensor network layouts and to understand the performance of these systems actually before they are built. So with that, I'd like to thank you for your attention. I'd be happy to answer any questions you may have. Thank you.